Well, hello, Mr. Naylor here. I wish I could have given this to you as a class challenge. It's fun to watch you guys talk out the answers to these 6 integrals. Plus, it helps you get ready for the test, which is going to have all these problems mixed up. Now, you will get a practice activity in the next post that will allow you to practice a whole bunch of these problems. But these 6 problems kind of give you a taste of the different methods we've studied and how and why they apply to each of these 6 integrals. Now, these first 2 here are meant to catch your attention as being similar yet significantly different. If you think about which one would require the substitution method, you'd be looking for an inside u whose du is going to cancel with the rest of the problem. And that familiar idea is going to happen if we let u equal 3x squared, because du is going to be 6x, a perfect cancellation with, again, the rest of the problem. So we can see here that this first one's going to be substitution. Now, the rule of thumb is if you can't use substitution, then it's going to be parts. And that's what's happening with this second one here. It's going to be a parts problem because we can't use substitution. And the reason we can't use substitution is because if we let the inside equal 3x, the derivative of that is going to only equal 3, and that is not going to cancel with this 6x. So the rule of thumb is if you can't use substitution, then you use parts. Now, moving on to this third one, again, it has 2 functions. It's got a cosine function and it's got a e to the x function. But once again, we have to ask ourselves, are we going to be able to use substitution? Because if you can't use substitution, then it's going to be parts. So before we make any decisions, think about u. I'm talking about an inside type of u. And if you let u equal e to the x, then the derivative is going to be the same thing. Now, that's a perfect cancellation with the rest of the problem, which is that other e to the x. So number 3 is going to be a substitution problem. Now, something like number 4, you can think of it as a substitution method, but it really doesn't matter because when you let the inside equal 4x minus 9, the derivative of that is only 4. What's going to end up happening is we're really going to end up dividing by 4, and ultimately that leads us to a basic situation where what we could have done is just divided by k, which again would be the same thing as dividing by 4. So we're going to argue that number 4 can be a basic problem because the inside is only going to have a derivative that's a number. Now, when you look at number 5, it really is a problem that you have to recognize as a special basic problem. The reason it's special is because it's going to be of the form 1 over 1 plus x squared. And if you can recognize that it's 1 over 1 plus x squared, then you'd be able to determine that number 5 is going to be an inverse tangent. So it ends up being a basic problem because we recognize. But if you compare that with number 6, you should see that we are not able to write it as 1 over 1 plus x squared. More specifically, it's a problem that has 2 functions, and one of the functions has a derivative that's going to be able to cancel with the 6x, specifically with the x, and so number 6 ends up being another substitution problem. So take a look at this little slide. It's a nice way to kind of organize your 3 ideas. Ultimately, basic is going to be a problem that you have to recognize. Also, there's really not 2 functions. There's only going to be 1 function in the problem. Now, the big question is substitution versus parts, and as we've been saying, you want to first think if you can use substitution, because if you can use substitution, then you need to use it so you can cancel out with that derivative. But if you can't use substitution, then it's going to be a parts problem. And, of course, if it is going to be a parts problem, we have to run the formula uv minus the integral of v du. Now, on the next slides, you're going to see me work out each problem. You may feel free to look at those slides. You can skip, you can try the problems first, and then check your answers. But each subsequent slide is going to be the worked out solution to each of these 6 problems. All right, so we decided that this first one's a substitution problem. You're going to let u equal 3x squared. The derivative is going to be 6x dx. If you do solve that, you can divide 6x to both sides. You don't have to divide this one if you don't want, because ultimately the 6x is going to cancel either way, so that you can change this to be a simpler problem, basically the sine of u du. Now don't forget to do the antiderivative. The antiderivative of sine is opposite cosine. It would be of u, but since u is 3x squared, we can substitute that back in. Don't forget your plus c, and you have your antiderivative. Now we said that number 2 was going to be a parts problem, so we're going to have to use the Lipit test. When you use the Lipit test, you're going to decide that you end up with the p, the power, so u equals the 6x function. That means dv is equal to the rest of the problem, and of course we have to go now to the derivative of u, which is 6 dx, but you have to do the antiderivative of v, which is going to be the opposite cosine of 3x divided by 3. Be careful, you have to divide by k since you're doing the antiderivative. Now we'll set up the formula so we can get our full answer here, which is uv. That's going to be a negative 6x cosine of 3x divided by 3. There is going to be some simplifying there, but that's your uv minus the integral of v du. Here I'm going to choose to put my 6 first, and of course I already got the negative sign from the opposite cosine, and also some simplifying we can do here, namely that you can turn that into 2. I'm going to go ahead and just do that now. We can change that to be 2 or negative 2 technically, and you also end up with a couple negative signs to turn to positive. You keep simplifying. It looks like you're going to be able to reduce slightly, but the main thing here is to actually do the antiderivative of 2 cosine of 3x. When you do the antiderivative of that, you're going to get the sine of 3x, but you have to divide by 3, which is dividing by k, which is ultimately going to put us with a 2/3 in front of that sign. Now I was looking at this third problem and I realized that it seems so tempting to try to use parts, but again, the reason you don't use parts is because you actually have a derivative, a du, that's going to cancel with the rest of this problem. So if we tried to use parts, we'd find out that we would get into an impossible situation, and that's because the problem is meant to be substitution. Again, it's going to be substitution because you end up with this derivative, namely e to the x, that's able to cancel with the e to the x that was in front. So we can cancel those, end up writing the problem as a simpler function, in other words, just one function, and now you can actually do the antiderivative of cosine. Remember, you want to do the antiderivative. That comes out to be sine, but we can fill in the u, which was e to the x. Don't forget your plus c. Now this square root problem, it is really just one function, but ultimately that one function is a 1/2 power. We might as well think of it as a 1/2 power because when you add 1 to this problem and start to do the antiderivative, you're really thinking like exponents. So we'll add to the exponent, add 1. When you add 1, that's the same as adding and getting 3/2. When you divide by 3/2, that's the same as 2/3. Now, the one thing here that you have to realize that there is a k value. That k value ends up being an extra coefficient, actually an extra coefficient that I have to divide by. So the order that I did this in is a little bit funny, but since I'm dividing by 3 and dividing by 4, that comes out to be 12, 2/12, which can reduce to be 1/6, 4x minus 9, which is to 3/2 power. Now we decided that we were going to somewhat rewrite and recognize this fifth problem as a 1 over 1 plus x squared. Of course, there's a 6 in front of it, but ultimately that allows us to do an inverse tangent. It's just of x. It's not the inverse tangent of x squared. That's because it's a rule, and that's all there is to it. All right, but if you compare that to this other fraction, there are two functions. There's a 6x function, there's an x squared plus 1 function, which means we want to think substitution. It is going to end up being substitution because the derivative of of x squared is 2x. Namely, the x right here is going to be able to cancel with this x beside the 6. So that's why we're going to use a substitution method. This time I'm going to show the actual substitution, meaning solving this problem, so that we can see the cancellation a little bit better. I'm going to end up with 1 over 2x dx when I substitute, or excuse me, du, when we substitute that in. So we're going to cancel these x's. We're also going to reduce the numbers so that we can end up with a simpler problem, namely 3 over u. Now recognize 3 over u as the same as a 1 over u, and anytime it's 1 over u, that's an ln. It's going to be the ln of u, but u of course was x squared plus 1. This is a good problem. It ends up that we use an ln in order to anti-derive this fraction.